Welcome to ancient Rome in the year 52 CE, during the reign of Emperor Claudius, when the city has grown to become the largest urban center the world has ever seen, home to perhaps 1 million people, all of whom require water for drinking, bathing, cooking, and the countless other uses that sustain urban life. For the next few hours, we will explore Rome's aqueduct system, the engineering marvels that bring water from distant sources to the heart of the city, the skilled workers who maintain these structures, the daily operations that keep water flowing, and the remarkable organizational systems that make it all possible. If you enjoy these detailed explorations of ancient engineering and daily operations, please like and subscribe to support our channel. Our story begins not in Rome itself, but in the hills east of the city, at the source of the Aqua Claudia, one of the most magnificent aqueducts ever built. The Claudia, completed just 6 years ago after 14 years of construction, brings water from springs in the Aniene Valley, approximately 45 miles from Rome, carrying it across valleys on soaring arches, through mountains and tunnels carved through solid rock, delivering it finally to reservoirs and fountains throughout the city. It is early morning, just after dawn, and we are standing at the source, a collection point called the Caput Aquae, where multiple springs has been channeled into a single stone basin that feeds the aqueduct's beginning. The water here is cold and pure, emerging from underground aquifers in the limestone hills, filtered by its passage through rock, pristine and clear. A water inspector named Sextus Julius Frontinus stands at the source, performing his daily inspection. Frontinus is not the famous Curator Aquarum, water commissioner, who will bear that name 40 years hence, but rather a minor official, one of many aquarii, water workers, employed by the imperial administration to maintain the aqueduct system. He is 40 years old, has worked for the water bureau for 15 years, and knows this section of the Claudia intimately, having walked its length hundreds of times. Frontinus begins his inspection by examining the collection basin. He checks the stone channels that direct spring water into the main basin, looking for any blockages from debris or sediment. He inspects the bronze gratings that filter out leaves and branches, ensuring they are clean and properly positioned. He examines the water level in the basin, comparing it to marks on the stone that indicate normal levels, assessing whether the springs are flowing at their expected volume. This morning, everything appears normal. The springs are producing their usual abundant flow. The Claudia's sources are among the most reliable in the region, providing consistent volume through all seasons. The water is clear, showing no signs of contamination or disturbance from upstream. The channels and gratings are clean, evidencing the work of the maintenance crew who cleaned them yesterday. Satisfied with the source's condition, Frontinus begins walking the aqueduct's course, following the channel as it descends gradually from the hills toward Rome. The first several miles are carried in a covered channel, a stone conduit approximately 3 feet wide and 6 feet high, just large enough for a man to walk through while inspecting. Frontinus carries a lamp. The channel is dark, lit only by occasional inspection shafts that pierce the roof, and he walks carefully, watching for any signs of problems. He looks for cracks in the stone lining, for seepage of water through the walls, for accumulations of sinter, calcium deposits from the water that might be restricting flow, for any damage from tree roots that have penetrated the structure. The channel is remarkably well built. The stones are precisely cut and fitted, creating a smooth surface that minimizes friction and allows water to flow efficiently. The gradient is carefully calculated. The Claudia descends at a rate of about 2 feet per mile, steep enough to maintain good flow, but not so steep that the water's velocity causes erosion or turbulence. This precision required sophisticated surveying during construction, using instruments like the chorobates, a leveling device, and the dioptra, a sighting instrument, to ensure accurate gradients across dozens of miles. As Frontinus walks, he makes notes on a wax tablet, recording the locations of any issues he observes, noting the condition of various sections, documenting work that will need to be done during the next maintenance cycle. The work is routine but essential. Aqueducts require constant attention. Left unmaintained, small problems become large ones. A tiny crack admits water that erodes surrounding stone. Tree roots penetrate and break channels. Sinter accumulates and eventually blocks flow. After approximately 2 miles, the underground channel emerges into daylight. transitioning to an above-ground arcade, a series of stone arches carrying the channel across a valley. This is the most visually impressive section of the Claudia, where the arches rise to heights of over 100 feet, marching across the landscape in perfect alignment, a monument to Roman engineering prowess. Frontinus emerges from the underground section and pauses, looking up at the towering arches. Even after 15 years of working with aqueducts, he finds them impressive. The scale is extraordinary. Each arch is made of massive stone blocks, fitted together without mortar in some sections, held in place purely by their own weight and the precision of their cutting. The highest tiers use lighter materials, including brick and concrete, reducing weight while maintaining strength. He begins walking along the top of the arcade, following the maintenance walkway that runs alongside the water channel. From this elevated position, he can see for miles the valley below with its farms and villages, the hills beyond, and in the distance, the unmistakable outline of Rome itself, the city that all this effort serves. The arcade requires different inspection techniques than the underground channels. Here, Frontinus looks for structural problems, cracks in the arches, signs of settling or movement in the piers, damage from weather or vegetation. He examines the joints between stones, checking that nothing has shifted. He inspects the water channel on top of the arches, looking for the same issues he checked underground: leaks, sinter deposits, blockages. At several points, he encounters other water workers, members of the maintenance crews who are constantly working on various sections of the aqueduct. A team of 4 men is chipping away sinter deposits from the channel walls. Hard physical work that requires chisels and hammers and considerable effort. Another team is repairing a section of the channel's roof that was damaged by a fallen tree branch. Yet another team is reinforcing a section of arcade where slight settling has been detected. Frontinus greets these workers, inspects their progress, offers guidance where needed. He is a supervisor as well as an inspector, responsible for coordinating the work of several crews across this section of the aqueduct. The workers are a mix of imperial slaves, freedmen employed by the Water Bureau, and private contractors hired for specialized work. They are skilled laborers. Working on aqueducts requires knowledge of stone, of hydraulics, of the specific challenges that water infrastructure presents. The conversation with the workers is brief and technical. How much sinter have you removed? About 3 wagon loads so far. This section was heavily deposited. Will you finish today? By sunset if we maintain this pace. Good. Make sure to clean up thoroughly. We can't have loose debris falling into the channel. This attention to detail, this constant maintenance work is what keeps the aqueducts functioning. Romans understand that these structures are not eternal monuments that, once built, will last forever without effort. They are working infrastructure that requires continuous care, constant investment of labor and resources, vigilant oversight. Frontinus continues his inspection, walking the entire visible length of the arcade, then descending to ground level where the aqueduct enters another underground section, burrowing through a hill rather than going over it. He will walk this underground section as well, inspecting every accessible part of this portion of the aqueduct, completing a routine he performs several times per week. The work takes most of the morning. By the time Frontinus completes his inspection and returns to the small station building, where the local aqueduct staff maintain their base of operations, the sun is high in the sky. He reviews his notes, prepares a written report for his superior, and dispatches it via courier to the main Water Bureau office in Rome. This daily inspection routine, multiplied across hundreds of miles of aqueducts and dozens of inspectors like Frontinus, is how Rome ensures its water supply remains constant and reliable. It is unglamorous work, invisible to most Romans who simply expect water to flow when they open a tap or visit a public fountain. But it is essential work, the foundation on which the city's water system, and therefore the city itself, depends. Frontinus eats his lunch, bread, cheese, and wine from his provisions, and prepares for the afternoon's work. Today he will supervise a crew cleaning one of the settling basins along the aqueduct's route, another routine maintenance task that prevents sediment from accumulating and reducing the system's capacity. The work of maintaining Rome's aqueducts never ends, a constant cycle of inspection, repair, cleaning, and vigilance that has continued since these structures were first built, and that will continue for as long as Rome endures. Let us now shift our attention from the aqueduct source to Rome itself, to the administrative heart of the water system, the offices of the Curator Aquarum, the water commissioner. located in the imperial bureaucracy's complex near the Forum. The current curator aquarum is a distinguished senator named Marcus Cocceius Nerva, grandfather of the future emperor. This position is one of significant prestige and responsibility. The curator oversees the entire aqueduct system, manages a staff of hundreds, controls a substantial budget, and reports directly to the emperor on matters concerning Rome's water supply. Nerva's office is a large room in the administrative complex, with walls covered by maps showing the aqueduct system, tables holding wax tablets and papyrus scrolls containing records and reports, and shelves filled with technical documents dating back decades. This is the nerve center of Rome's water infrastructure, where information flows in from hundreds of inspectors and maintenance workers across the system, where decisions are made about repairs and improvements, where the daily operations of the most sophisticated urban water system in the ancient world are coordinated. This morning, Nerva is meeting with his chief engineer, a Greek freedman named Vitruvius, not the famous architect and engineer who wrote De Architectura, but a man who shares his name and profession. They are reviewing reports from across the system, identifying problems that require attention, planning maintenance work for the coming months. The Aqua Marcia shows reduced flow at the terminal reservoir, Vitruvius reports, referring to the oldest of Rome's major aqueducts, built over 200 years ago. The inspectors suspect sinter accumulation in the underground sections near Tivoli. I recommend scheduling a major cleaning operation, perhaps 2 weeks of work with a crew of 20 men. Nerva considers this. The Marcia is one of Rome's most important aqueducts, supplying water to many of the city's highest elevation points. Reduced flow is a serious concern. But major cleaning operations are expensive and disruptive, requiring sections of the aqueduct to be shut down while work proceeds. Can we afford to take the Marcia offline for 2 weeks, he asks. If we do it in late autumn, when water demand is lower, and if we increase flow from the Claudia and the Anio Novus to compensate, yes. We'll have adequate total supply, though some distribution adjustments will be needed. Draft the work plan. I'll review it before authorizing the expenditure. They move to the next issue, a report from inspectors on the Aqua Tepula, indicating foundation settlement in one section of arcade. This is potentially serious. If the settlement continues, it could crack the arches, possibly leading to structural failure. How extensive is the settlement? Nerva asks. Inspectors report movement of approximately 2 digits over the past year. A digit is about 3/4 of an inch, so roughly 1.5 inches of settlement. That's concerning. What do you recommend? We should shore up the foundations before further settlement occurs. I propose excavating around the affected piers, reinforcing the foundations with additional stonework and concrete, and monitoring the situation closely for the next several years. How much will this cost? Approximately 15,000 sestertii for materials and labor. Nerva winces slightly. This is a substantial sum, though not enormous by the Water Bureau's budget standards. But costs accumulate, the Marcia cleaning, the Tepula foundation work, and these are just 2 of dozens of ongoing maintenance projects across the system. Authorized, but try to bring it in under budget if possible. The Emperor is concerned about infrastructure costs. He's receiving pressure from senators who think we spend too lavishly on public works. This political dimension of water management is a constant reality. The aqueducts are expensive to maintain, and there are always voices arguing that the money could be better spent elsewhere. On military campaigns, on grain subsidies, on games and spectacles. The curator must balance technical necessity against political pressure, must justify expenditures, must sometimes accept deferred maintenance because funding is unavailable. The meeting continues through the morning, reviewing reports, making decisions, planning work. The scope of the Water Bureau's operations is staggering. Rome now has 9 major aqueducts bringing water from various sources, totaling over 300 miles of channels, arcades, and tunnels. The Bureau employs over 700 workers, from skilled engineers and inspectors to laborers who do the physical work of maintenance and repair. Managing this system requires sophisticated administrative capabilities. The Bureau maintains detailed records, measurements of flow rates from each aqueduct, documentation of maintenance work performed, inventories of materials and tools, payroll records for workers, contracts with suppliers and contractors. This information must be collected, organized, and analyzed to make informed decisions about resource allocation and work priorities. After the engineering meeting, Nerva meets with his chief accountant to review the budget. The Water Bureau's annual budget is substantial, over 3 million sesterti per year, funded from imperial revenues. The largest expenses are labor costs and materials: stone, lead for pipes, bronze for valves and fittings, cement and concrete for repairs. The accountant presents a summary of year-to-date expenditures, comparing them to the approved budget. Some categories are under budget, others are over, but overall spending is tracking close to plan. Nerva approves a series of payments to contractors and authorizes the purchase of materials for upcoming projects. This financial management is crucial. The Water Bureau must operate within its allocated budget while ensuring adequate maintenance of the system. Underspending might seem fiscally responsible, but can lead to deferred maintenance and future problems. Overspending invites political criticism and can jeopardize future funding. After the budget meeting, Nerva receives a delegation of property owners from the Esquiline Hill who are complaining about water pressure in their neighborhood. They claim they are entitled to higher flow rates based on their tax payments and social status, and they demand that the Water Bureau increase supply to their district. This is a delicate situation. Water distribution in Rome is highly political. The wealthy expect abundant water for their homes, their baths, their gardens. But the system has finite capacity, and increasing supply to one area often means reducing it elsewhere. Moreover, some wealthy Romans have bribed previous water commissioners to grant them illegal connections or higher allocations than they are entitled to, creating inequities in the distribution system. Nerva listens politely to the delegation's complaints, consults his records about current allocations to the Esquiline, and explains that their neighborhood already receives water supply proportional to its population and legal entitlements. He cannot simply increase their allocation without justification. The delegation is not satisfied. They imply that the previous curator was more accommodating. They hint that Nerva's inflexibility might be remembered unfavorably by influential senators. They suggest that perhaps a private arrangement could be reached. Nerva remains firm. Gentlemen, the aqueducts serve the entire city. Water must be distributed according to law and need, not according to who can offer the largest bribes. If you believe your allocation is insufficient, you may petition the emperor. But I will not alter distributions to favor one neighborhood over another based on political pressure or personal inducements. The delegation departs, clearly displeased. Nerva knows this will create political problems for him. These are influential men who can cause trouble. But he also knows that maintaining the integrity of the distribution system is essential. Once he starts making special arrangements for powerful individuals, the system will quickly devolve into corruption and favoritism, undermining its ability to serve the city fairly. This confrontation illustrates a crucial aspect of managing Rome's aqueducts. It is not purely a technical challenge, but also a political one. The curator must navigate relationships with the emperor, with the Senate, with wealthy Romans who want special treatment, with the general public who depend on the system functioning properly. Technical competence is necessary, but not sufficient. Political skill is equally important. After the delegation leaves, Nerva takes a moment to reflect on the challenges of his position. He is responsible for one of the most critical systems in Rome, a system on which 1 million people depend for their daily water needs. He must ensure the aqueducts remain in good repair, that water is distributed fairly, that the budget is managed responsibly, that political pressures do not compromise technical integrity. It is demanding work, but it is also important work. Nerva takes pride in the responsibility, sees his service as a contribution to the public good. He is wealthy enough that he does not need the position's modest salary. He serves because service to the state is what distinguished Romans are expected to do. Because managing critical infrastructure is honorable work. Because ensuring that Rome's people have access to clean water is a worthy way to spend one's time and energy. As afternoon approaches, Nerva prepares for a field inspection. Despite his administrative duties, he believes it is important to personally inspect the system regularly, to see firsthand the conditions on the ground, to ensure that the reports he receives accurately reflect reality. Today he will visit one of the major distribution points where the Aqua Claudia enters the city, observing the operations there, talking with workers, assessing whether improvements are needed. He gathers his documents and his staff and departs the office, making his way through Rome's crowded streets toward the Claudia's terminal point on the Caelian Hill, where the Aqueducts water is distributed to various parts of the city through a complex network of reservoirs, tanks, and pipes. The point where an aqueduct enters the city is a marvel of hydraulic engineering, a carefully designed system for taking the aqueduct's single stream of water and dividing it among multiple uses and users, maintaining pressure and flow, ensuring fair distribution according to legal allocations. The Aqua Claudia's main distribution point, called a Castellum Aquae, or water castle, is a large stone structure on the Caelian Hill, one of Rome's 7 hills. The aqueduct's channel enters the castellum at a high level, and the water then flows into a series of settling tanks, where sediment can fall out before the water is distributed further. From the settling tanks, the water flows to the distribution chamber, a large room containing a series of pipes and valves that direct water to different destinations. Some water goes to public fountains scattered throughout the city. Some goes to the imperial palace and to wealthy private residences that have paid for private connections. Some goes to the public baths. Some goes to commercial establishments like fulling workshops that use large quantities of water for processing cloth. A water bailiff named Gaius Flavius oversees this distribution point. He is responsible for ensuring that water is distributed according to the official allocations, that illegal taps are detected and removed, that the distribution equipment is maintained and functioning properly. He supervises a staff of 10 men who operate valves, monitor flows, perform maintenance, and patrol the distribution network to detect problems. When Nerva arrives for his inspection, Flavius greets him respectfully and begins showing him around the facility. They start in the settling tanks, where Flavius explains the cleaning schedule. The tanks are drained and cleaned every 2 weeks, a labor-intensive process that requires diverting flow to alternate tanks while work proceeds. How much sediment accumulates in 2 weeks? Nerva asks. Perhaps 2 or 3 cartloads, depending on conditions upstream. The Claudia's water is fairly clean, but some sediment is inevitable. They move to the distribution chamber, where Flavius shows Nerva the various pipes and their associated valves. Each pipe is marked with a bronze tag, indicating its destination and legal allocation. The system is ingenious. The pipes are sized precisely to deliver specific flow rates, and the laws specify that allocations are determined by pipe diameter, measured in units called calyx, literally drinking cups. A standard pipe delivering water to a public fountain might be 5 calyx in diameter. A private connection to a wealthy household might be 2 or 3 calyx. The imperial palace has connections of 10 or even 20 calyx. These pipe sizes determine how much water each recipient receives, and they are specified in official documents that Flavius keeps locked in an iron chest. But maintaining this system of legal allocations is challenging. Wealthy Romans constantly attempt to gain unauthorized water, illegally enlarging their pipes, installing secret taps, bribing water officials to grant them higher allocations than they are entitled to. Flavius must be constantly vigilant, inspecting private connections, verifying that pipe sizes match official records, detecting and removing illegal taps. How many illegal connections have you found this month? Nerva asks. 7. 3 enlarged pipes, 4 completely unauthorized taps. We removed them all and assessed fines on the property owners. Did they pay the fines? 2 paid. The others are contesting. One claims his grandfather was granted the connection and that it's therefore legal, though he has no documentation. Another claims the connection is for a public purpose, supplying water to his household staff, and should therefore be exempt from restrictions. Nerva shakes his head. These excuses are typical. Wealthy Romans always have creative justifications for why they should receive special treatment. Uphold the fines. If they want to contest, they can petition through proper channels. Do not restore their water until the fines are paid or they receive official authorization. They continue the inspection, moving outside to examine the distribution network of pipes that carries water from the castellum to various parts of the city. This network is extensive and complex. Primary pipes of lead or ceramic branching into secondary pipes, which branch further into smaller distribution pipes, creating a tree-like structure that delivers water throughout the district. The pipes are mostly underground, buried beneath streets or running through tunnels. Access points at regular intervals allow workers to reach the pipes for inspection and maintenance. Flavius shows Nerva one such access point, a small shaft with a wooden cover that, when removed, reveals a lead pipe about 6 inches in diameter, running beneath the street. "How often do you inspect the underground network?" Nerva asks. "We try to inspect all major pipes at least quarterly. We inspect based on complaints. If someone reports low pressure or no flow, we trace that line immediately." What are the most common problems? Pipe corrosion, especially in the lead pipes, blockages from debris or mineral deposits, breaks from ground settling or from construction work that inadvertently damages the pipes, and leaks. Joints between pipe sections sometimes fail. The underground pipe network is perhaps the most vulnerable part of the entire system. Unlike the aqueducts themselves, which are massive stone structures built to last centuries, the pipe networks are made of materials, lead, ceramic, wood in some cases, that deteriorate relatively quickly. Pipes must be replaced periodically, joints must be maintained, leaks must be repaired promptly. Nerva is particularly concerned about lead pipes. Lead is widely used because it is malleable, can be easily worked into pipes and joints, and is reasonably durable. But some physicians have suggested that lead may be harmful to health, and there are reports of workers in lead mines developing strange maladies. Nerva has been considering whether Rome should transition away from lead pipes towards ceramic or stone alternatives, but such a transition would be enormously expensive and disruptive. Lead pipes are entrenched in the system, and replacing them would require years of work and vast expenditure. For now, lead pipes remain standard, though Nerva has ordered that new public fountains be supplied with ceramic pipes where possible, gradually shifting away from lead for the most public uses. The inspection continues through the afternoon. Nerva examines public fountains, checking that they are flowing properly and that the water is clean and clear. He visits a public bath, observing how it receives and uses its water allocation. He inspects private connections to several wealthy households, verifying that they match official records. At one such household, he discovers a discrepancy. The pipe is clearly larger than the 2-calyx size recorded in the official allocation. When confronted, the household steward claims ignorance, suggesting that perhaps the previous owner enlarged the pipe, that the current owner knew nothing about it. Nerva is skeptical, but cannot prove deliberate fraud. He orders the pipe replaced with the correct size and assesses a fine for unauthorized water use. The steward protests, threatens to complain to his master, who is an influential senator. Nerva remains firm. The law is clear, and it applies to everyone, regardless of wealth or political connections. This confrontation, like the earlier one in his office, illustrates the constant political challenges that come with managing water distribution. The wealthy feel entitled to abundant water and resent restrictions. They use their influence to pressure water officials to seek exceptions and special treatment. Maintaining fair distribution requires constant vigilance and willingness to withstand political pressure. As evening approaches and the inspection concludes, Nerva returns to his office to prepare reports and recommendations. He has identified several issues that require attention: pipes that need replacement, illegal connections that must be pursued more aggressively, improvements to the distribution castellum that could improve efficiency. But overall, the system is functioning well. Water is flowing to all parts of the city. The public fountains are operating, providing free water to Rome's masses. The baths are supplied, enabling the daily ritual of bathing that is so central to Roman social life. The wealthy have their private supplies, though Nerva is working to ensure these comply with legal limits. The aqueducts and their distribution systems are one of Rome's greatest achievements, engineering marvels that make urban life possible on an unprecedented scale. Nerva takes pride in his role in maintaining this system, in ensuring that Rome's people continue to have access to the abundant, clean water that distinguishes their city from all others in the ancient world. As night falls and Nerva finally leaves his office, he looks out over Rome, a city of nearly 1 million people, most of whom are going about their evening routines without giving a thought to where their water comes from or how it reaches them. This invisibility is, in a way, the ultimate measure of success. The system works so well, so reliably, that people take it for granted. And maintaining that reliability is what Nerva and hundreds of workers like him dedicate their professional lives to accomplishing. while administrators like Nerva manage the system from offices and inspectors like Fontinus patrol the aqueduct channels. Another group of specialists performs one of the most skilled and hazardous jobs in water system maintenance: the plumbari, the lead workers, who fabricate and install the lead pipes that carry water throughout the city. Let us visit one of the lead workshops located in the Subura, Rome's crowded working-class district. The workshop is owned by a freedman named Marcus Pontius Crescens, who learned the plumber's trade as a slave, and after earning his freedom, established his own business fabricating and installing lead pipes for the Water Bureau and the private customers. The workshop is a long, narrow building with a furnace at one end where lead is melted and a workspace where pipes are fabricated. The heat from the furnace makes the workshop stifling, even in winter, and the lead workers are stripped to the waist despite the cold outside, their bodies streaming with sweat as they work. Crescens employs 6 workers, 4 slaves whom he owns, an apprentice who is a free youth learning the trade, and a journeyman who is a skilled freedman working for wages. Together they produce perhaps 10 linear feet of pipe per day, depending on the diameter and complexity of the work. The process of making lead pipe is skilled and dangerous work. It begins with lead ingots, which are melted in the furnace at temperatures exceeding 600 degrees Fahrenheit. The molten lead is poured into molds or onto flat sheets, which are then worked while still hot, shaped into pipe sections, and joined using molten lead as solder. The danger comes from the lead itself. The workers breathe lead fumes from the furnace and from the molten metal. Lead dust coats their skin and clothes. Despite washing at the end of each day, they inevitably ingest some lead, and over time this exposure causes illness. The lead workers often develop tremors, weakness, cognitive problems, and premature death. Crescens is aware of these dangers. He has seen workers sicken and die, has experienced some symptoms himself. But lead working is his trade, his livelihood, and he knows no other way to make a living. He tries to minimize the risks, ensuring good ventilation in the workshop, having workers wash frequently, providing them with protective garments. But these measures offer only limited protection. This morning, the workshop is fulfilling a contract from the Water Bureau, producing pipes for a new distribution line being constructed in the Aventine district. The pipes must be precisely fabricated to specifications provided by the Bureau's engineers, with exact diameters to ensure proper flow rates. One of the slave workers, a man named Fortunatus, is shaping a pipe section. He takes a flat lead sheet that has been cast from molten metal and carefully wraps it around a wooden mandrel, a cylindrical form that gives the pipe its shape and diameter. He hammers the edges of the sheet together, creating a seam that runs the length of the pipe, then solders the seam using molten lead applied with a bronze ladle. The work requires skill and precision. The seam must be perfectly straight and completely sealed. Any gaps will cause leaks when the pipe is pressurized. The diameter must match the specification exactly. Even small variations can affect flow rates and cause problems when connecting pipe sections together. Fortunatus has been doing this work for 8 years and has developed considerable skill. His seams are neat and solid, his diameters consistent. But the work takes its toll. He has developed a persistent tremor in his hands, and he sometimes experiences confusion and memory problems. He is 32 years old, but looks older, his body aged by the harsh conditions of lead work. After fabricating the pipe section, Fortunatus passes it to another worker, who will cut it to the precise length specified in the contract, and create the joint fittings that allow it to connect to adjacent pipe sections. This worker uses saws and files to shape the lead with remarkable precision, creating joints that will fit tightly and seal properly when installed. The completed pipe sections are inspected by Crescens, who checks dimensions, tests the seams for soundness, and ensures that each piece meets the contract specifications. Substandard work will be rejected by the Water Bureau inspectors, and Crescens' reputation depends on consistent quality. Once approved, the pipes are loaded onto carts for transport to the installation site. A crew of laborers, supervised by a senior plumber from Crescens' workshop, will take the pipes to the Aventine, excavate trenches, install the pipes, test them for leaks, and backfill the trenches. This installation work is physically demanding and requires its own specialized skills. Pipes must be properly supported to prevent sagging, joints must be carefully made to avoid leaks, the grade must be correct to ensure proper flow. While Crescens's workshop produces pipes, another specialized workshop nearby produces other lead components for the water system: valves, fittings, connection pieces, repair patches. The variety of components is considerable, and each requires specialized knowledge to fabricate correctly. The economics of leadworking are challenging. The raw material, lead ingots, is expensive, though less so than bronze or other metals. The skilled labor is costly. Even slaves must be purchased and maintained, and free workers command wages reflecting their specialized skills. The workshop's overhead, rent, fuel for the furnace, tools and equipment, adds further costs. Crescens charges the Water Bureau approximately 20 sesterti per linear foot of installed pipe, depending on diameter and complexity. This price must cover his materials, labor, overhead, and profit. The margins are modest, and he must maintain a steady flow of contracts to keep his workers employed and his business viable. But there is also considerable demand. Rome's water system is constantly being expanded and repaired, requiring continuous production of new pipes. Wealthy Romans want private connections to their homes and baths. Public buildings need water supply. The market for lead pipes is robust, and a competent plumber can make a decent living. Crescens has ambitions beyond his current operation. He hopes to expand his workforce, to take on larger contracts, perhaps to bid on major Water Bureau projects that would bring prestige and substantial profits. But expansion requires capital. Money to purchase more slaves or hire more free workers, to buy larger quantities of raw materials, to rent additional workspace. He is saving his profits, building capital slowly, hoping eventually to achieve the expansion he envisions. It is a common dream among Roman entrepreneurs to start small, to grow gradually through competent work and saved profits, to eventually achieve significant business success. As midday approaches, Crescens calls a break. The workers emerge from the stifling workshop into the relatively cool air outside, grateful for the respite. They drink water heavily. The heat and the lead exposure make them constantly thirsty. They eat a simple meal of bread and cheese purchased from vendors in the Sabura's crowded streets. The conversation among the workers is muted. The lead workers are not a cheerful group. Their work is hard, their health is poor, their prospects are limited. But they share a camaraderie born of shared hardship, an unspoken understanding of the difficulties they face. After the meal, work resumes. The afternoon will be much like the morning, melting lead, shaping pipes, soldering seams, inspecting finished products. The rhythm is steady and repetitive, broken only by occasional problems that require problem solving, or by visits from customers who come to discuss projects or inspect work. As evening approaches, and the day's work nears its end, Crescens tallies the day's production. 8 pipe sections completed, meeting the day's quota for the Water Bureau contract. The workers clean the workspace, bank the furnace fire, wash themselves as best they can to remove lead dust and residue. They disperse to their homes, or in the case of the slaves, to their quarters in Crescens's household. Another day of lead work is complete, one of thousands of such days that these men will experience over their working lives, contributing to Rome's water infrastructure through their skilled and dangerous labor. The lead workers are rarely celebrated or even noticed. They are not engineers like Vitruvius, not administrators like Nerva, not even inspectors like Frontinus. They are craftsmen performing dangerous, unglamorous work, producing the components that make the distribution system function. The aqueduct system could not work. The grand arcades bringing water from distant sources would be impressive but useless without the distribution networks that carry water throughout the city. The pipes that these lead workers fabricate, install, and maintain are as essential to Rome's water supply as the aqueducts themselves, though they are buried underground, invisible, forgotten by all except those who make and maintain them. This is the reality of infrastructure. It depends not just on grand engineering and administrative competence, but on the daily labor of countless workers performing unglamorous, often dangerous tasks, building and maintaining the systems that make urban civilization possible. It is late evening, well after sunset, and most of Rome is settling into its nighttime routines. But at the Water Bureau's Emergency Response Center, a station manned around the clock to handle urgent problems, A report has just arrived of a major pipe break in the Esquiline district. Water is flooding into the street, and several buildings are being damaged. An emergency repair crew must be dispatched immediately. The crew chief is a veteran water worker named Lucius Sergius, a freedman who has worked for the Water Bureau for 25 years and has handled countless emergencies. He receives the report, assembles his crew of 6 men, and loads their equipment onto a cart. Tools, lead sheets for patching, torches for illumination, timber for shoring up excavations. They make their way through Rome's dark streets toward the Esquiline, navigating by the light of torches and by their knowledge of the city's layout. The streets are quieter at night, but not empty. Rome never completely sleeps. They encounter late-night travelers, watchmen making their rounds, prostitutes soliciting customers, beggars sleeping in doorways. When they arrive at the break site, the situation is as reported. Water is gushing from beneath the street, flooding the area, flowing downhill in a small river. Several irate property owners are waiting, demanding that the Water Bureau fix the problem immediately, complaining about damage to their property, threatening legal action. Sergius assesses the situation quickly. This is a major break in a primary distribution pipe, probably caused by ground settling or by the pipe's age and corrosion. Fixing it will require locating the exact break point, excavating to expose the pipe, assessing the damage, and either patching or replacing the broken section. First, the flow must be stopped. Sergius dispatches 2 of his men to the nearest control valve, where they can shut off flow to this section of pipe. This will stop the flooding, but will also cut off water to everyone downstream of the valve, affecting perhaps several hundred households. The decision to shut off flow is not taken lightly, but in this case, there is no alternative. The pipe cannot be repaired while water is gushing through it. While the men are shutting the valve, Sergius organizes the excavation. His crew begins digging up the street, removing paving stones, excavating the earth beneath to expose the pipe. The work is hard and must be done carefully. The pipe is buried about 4 feet deep, and the excavation must be properly shored to prevent collapse. By torchlight, the crew works steadily, removing soil, constructing timber supports, gradually exposing the pipe. After about an hour, they have opened a section about 10 feet long, and the break is visible, a split in the lead pipe, perhaps 6 inches long, probably caused by corrosion that weakened the pipe wall until pressure finally caused it to rupture. Sergius examines the break, assessing whether it can be patched or whether a section of pipe must be replaced. He decides on replacement. The pipe is old and corroded, and a patch would likely fail soon. Better to replace this section now than to return in a few weeks for another repair. But replacing the pipe section is complex work, especially at night by torchlight. The damaged section must be cut out, a new section must be fabricated or obtained from stores, the new section must be installed and its joints sealed properly. This will take several hours, and it cannot be rushed. Improper installation would cause leaks and future problems. Fortunately, Sergius's crew is experienced and well-equipped. They have prefabricated pipe sections of various sizes in their equipment stores, including one that matches the diameter of this broken pipe. They also have the tools and materials needed to cut the old pipe, install the new section, and create proper sealed joints. The work proceeds methodically. The damaged section is cut out using saws and chisels. The new section is measured, cut to exact length, and positioned in place. The joints are created by forming overlapping connections and sealing them with molten lead applied carefully to create watertight seams. This soldering work is particularly challenging at night. The lead must be heated to the proper temperature, hot enough to flow and bond, but not so hot that it damages the existing pipe. The work must be done by torchlight, requiring steady hands and careful attention, despite the difficult conditions. Throughout this process, Sergius coordinates his crew, inspecting their work, making adjustments as needed, ensuring that proper procedures are followed. He has done this hundreds of times, but he never takes it for granted. Each repair is critical, and mistakes can cause worse problems than the original break. As the repair work continues, the property owners watch impatiently, still complaining about the water damage to their buildings, demanding compensation, threatening legal action. Sergius listens politely, but continues working. His job is to fix the pipe, not to negotiate with angry citizens. The Water Bureau has procedures for handling damage claims, and those procedures will be followed, but they are not his responsibility. After approximately 3 hours of work, the new pipe section is installed, the joints are sealed, and Sergius is ready to test the repair. He signals to the crew members at the control valve, and they gradually open it, allowing water to flow through the repaired section. Everyone watches tensely as pressure builds in the pipe. Will the joints hold? Are there any leaks? The new section is tested under full pressure, and for several minutes, Sergius and his crew carefully inspect every inch of the work, looking for any sign of seepage or weakness. The repair holds. No leaks are visible. The joints are sound. Sergius allows himself a moment of satisfaction. Another successful emergency repair. Another crisis averted. But the work is not yet complete. The excavation must be backfilled. The street must be repaved. The site must be cleaned up. This work will wait until daylight. Right now it is sufficient to backfill loosely and mark the site with barriers so no one falls into the excavation. A regular crew will return tomorrow to complete the restoration properly. As dawn begins to lighten the eastern sky, Sergius and his crew pack up their equipment and return to the emergency response center. They are exhausted. The physical work, the stress of performing complex repairs under difficult conditions, the late hour, all combine to leave them drained. But they are also satisfied. They have performed essential work, have restored water service, have prevented worse damage from the flooding. This is what they do, what they have trained for, what they take pride in. Sergius will file a report describing the break, the repair, and the time and materials required. This information will go into the Water Bureau's records, contributing to the knowledge base about pipe failures and helping engineers plan future maintenance and replacement programs. The crew members will get a few hours of rest before returning to their regular duties. Emergency repairs are unpredictable. They might go weeks without a major incident, or they might face several emergencies in rapid succession. The crew must always be ready, must maintain their skills and equipment, must be prepared to respond at any hour of day or night. This emergency response capability is another essential element of Rome's water system. Despite all the preventive maintenance, despite regular inspections and routine repairs, emergencies still occur. Pipes break, aqueduct channels crack, distribution systems fail. Having trained crews ready to respond quickly minimizes disruption and prevents small problems from becoming large ones. As Sergius finally reaches his home and collapses onto his bed, exhausted but satisfied with the night's work, he reflects that this is the unglamorous reality of maintaining Rome's water infrastructure. Most people never see this work, never know about the midnight emergencies and the skilled repairs performed under difficult conditions. They simply expect water to flow, and when it doesn't, they complain about the disruption. But Sergius and his fellow water workers know the truth. Maintaining a complex infrastructure system requires constant vigilance, skilled labor, willingness to work under difficult conditions, and dedication to keeping the system functioning, regardless of the challenges. It is not glorious work, but it is essential work, and Sergius takes pride in doing it well. As we conclude our exploration of Rome's aqueduct system, let us step back and consider the broader significance of these engineering marvels. What they tell us about Roman civilization, how they functioned as both technical systems and social institutions, why they mattered then, and why they continue to matter now. The aqueducts were, first and foremost, solutions to practical problems. Rome grew to become the largest city in the ancient world, with a population that eventually exceeded 1 million people. Such density of population created challenges that no city had previously faced, and water supply was among the most critical. Natural water sources within the city, the Tiber River, local springs and wells, were inadequate to meet demand. The Tiber was polluted by sewage and industrial waste, making it unsuitable for drinking. Local sources could supply a small town, but not a metropolis. Without imported water, Rome could not have grown as large as it did. The aqueducts solved this problem by bringing water from clean, abundant sources in the hills surrounding Rome, carrying it across distances up to 60 miles, delivering it in quantities sufficient to supply 1 million people. The scale of this achievement was unprecedented. No previous civilization had built water infrastructure on this scale, or with this degree of sophistication. But the aqueducts were more than just utilitarian infrastructure. They were also expressions of Roman power and identity, monuments to Roman engineering prowess, visible demonstrations that Rome could accomplish what other civilizations could not. The great arcades carrying water across valleys were deliberately monumental, built to impress, to display Roman capability to Romans and to subject peoples alike. This symbolic dimension mattered. Romans took pride in their aqueducts, saw them as evidence of Roman superiority, celebrated them in literature and art. The historian Pliny the Elder called the aqueducts the most noteworthy achievement anywhere in the world, and this was a common Roman sentiment. The aqueducts were proof that Roman civilization was advanced, sophisticated, capable of grand achievements. The engineering principles underlying the aqueducts were not themselves particularly advanced by modern standards. The Romans did not invent the aqueduct. Earlier civilizations, including the Assyrians and the Greeks, had built water channels. What made Roman aqueducts exceptional was the scale on which these principles were applied, the precision with which they were executed, and the organizational capacity required to build and maintain such systems. The public baths, supplied by aqueduct water, became central institutions of Roman social life. Romans bathed daily, using the baths not just for cleanliness, but for socializing, exercising, conducting business, relaxing. The baths were subsidized by the state and charged minimal entrance fees, making them accessible to all classes. This universal access to bathing facilities was unique in the ancient world and contributed to Romans' sense of superiority over barbarians who did not bathe regularly. Private water connections, while restricted primarily to the wealthy, also had social significance. Having running water in one's home was a status symbol, a visible marker of wealth and privilege. The ability to have private baths, fountain courts, and irrigated gardens within one's house demonstrated social position in ways that enhanced the stratification of Roman society. The political management of water distribution, the conflicts we saw between Nerva and wealthy Romans seeking special treatment, illustrates how infrastructure became a site of political struggle. Water was power, and controlling its distribution conferred authority. The curator aquarum, despite being a technical administrator, wielded significant political influence because he controlled access to a critical resource. The economic impact of the aqueducts was also substantial. The construction and maintenance of the system employed thousands of workers, engineers, surveyors, stonecutters, masons, plumbers, laborers. The lead working industry, as we saw with Crescens's workshop, created jobs and economic activity. The availability of abundant water enabled industries that required large water quantities: fulling, dyeing, food processing. The baths employed many workers and supported related businesses. But the aqueducts also represented significant costs. Construction was enormously expensive. Ancient sources suggest that major aqueducts cost tens of millions of sestertii to build, equivalent to substantial fractions of the imperial budget. Maintenance costs, while smaller, were ongoing and substantial. These costs were justified by the benefits, but they also meant that resources spent on aqueducts were not available for other purposes. The technology of Roman aqueducts spread throughout the empire. Wherever Romans built cities, they built aqueducts, in Gaul, in Spain, in North Africa, in Asia Minor. Some of these provincial aqueducts survive today, still impressive nearly 2,000 years after their construction. The Pont du Gard in France, the Segovia Aqueduct in Spain, these are among the most iconic Roman ruins, visited by millions of modern tourists. But the aqueduct systems also illustrate the fragility of complex infrastructure when political and economic conditions change. As the Roman Empire declined in the West during the 5th and 6th centuries, aqueduct maintenance systems broke down. The trained workers died or fled, the administrative systems dissolved, the resources to fund maintenance disappeared. The aqueducts gradually failed, not all at once in dramatic destruction, but slowly, through accumulated deferred maintenance, through breaks that were not repaired, through sinter accumulation that was not removed. By the early medieval period, most of Rome's aqueducts had ceased functioning. Rome's population declined from its peak of over 1 million to perhaps 30,000, a devastation made possible partly by the loss of the water supply. The city that once boasted of providing abundant clean water to 1 million people became a shadow of itself, its inhabitants drawing water from the polluted Tiber and from a few still functioning wells, living among the ruins of infrastructure they could no longer maintain. This collapse was not inevitable. Some aqueducts in other parts of the former empire continued functioning for centuries after the Western Empire fell. But it illustrates an important truth about infrastructure. Technical capability alone is insufficient. Infrastructure requires institutions, resources, trained personnel, political will to maintain it. When these supports dissolve, even the most magnificently engineered systems will fail. The eventual rediscovery and restoration of some ancient Roman aqueducts, particularly the restoration of the Aqua Virgo in the Renaissance, demonstrated both the durability of Roman engineering and the continuing relevance of Roman hydraulic principles. The restored Aqua Virgo still supplies water to Rome's Trevi fountain, a direct link between ancient and modern water infrastructure. Modern water engineers studying Roman aqueducts have been impressed by the sophistication of Roman hydraulic engineering, the precision of gradients, the clever solutions to engineering challenges, the scale of construction. While modern technology enables capabilities Romans could not achieve, the fundamental principles Romans applied, gravity flow, careful surveying, quality construction, systematic maintenance, remain relevant to modern water infrastructure. The legacy of Roman aqueducts extends beyond engineering to questions of governance and public goods. The aqueducts demonstrate that complex urban societies require sophisticated infrastructure, and that providing such infrastructure is a legitimate function of government. The Romans understood that some goods, clean water, sewers, roads, must be publicly provided because private provision would be inadequate or inequitable. This Roman understanding, sometimes forgotten in later eras, has become conventional wisdom in modern times. We expect governments to provide water infrastructure, to maintain it through tax revenues, to ensure universal access at affordable prices. This model of infrastructure as a public responsibility, funded collectively and managed by specialized bureaucracies, owes much to Roman precedents. As we conclude our exploration, let us return once more to the Aqua Claudia, to the point where we began, the source in the Aniene Valley, where clear water emerges from limestone springs. The Inspector Frontinus is completing another day's walk along the aqueduct, performing the same routine inspections he has done hundreds of times, ensuring that water continues to flow, that the system remains in good repair, that Rome's people have the water they need. This daily routine, this unglamorous but essential work, is what makes the aqueducts function. The grand arcades and the sophisticated engineering matter, but they would be useless without the constant maintenance, the skilled repairs, the administrative oversight, the dedicated labor of workers like Frontinus and Sergius and Crescens, and hundreds of others whose names history has not recorded. The aqueducts of Rome are monuments to human capability, to our ability to identify problems and create solutions, to build on massive scales, to organize complex systems, to maintain infrastructure across generations. They demonstrate what human societies can accomplish when they commit resources and expertise to solving collective challenges, when they create institutions to manage complex systems, when they accept the ongoing responsibilities that infrastructure requires. But they also remind us of the fragility of such achievements, of how quickly complex systems can fail when the institutions and resources that support them dissolve, of how what one generation builds, another generation can lose through neglect or inability to maintain. The aqueducts brought water to Rome for over 1,000 years, supporting the greatest city of the ancient world, enabling a level of urbanization and civilization that would not be matched again until modern times. They were engineering marvels, certainly, but they were also social and political achievements, products of Roman organizational capability and willingness to invest in public goods. As the sun sets over the Claudius source and Frontinus completes his inspection and heads home, the water continues to flow, as it has flowed for centuries, carrying life and civilization from the hills to the city, a constant stream linking source to destination, past to present, the ancient engineers who designed these systems to the modern people who still draw inspiration from their achievements, the workers who maintain infrastructure to the people who depend on it, all connected by the simple yet profound fact of water flowing through channels cut and built by human hands, serving human needs, sustaining human civilization, demonstrating that we can, when we choose, accomplish remarkable things, create systems that endure, build infrastructure that serves not just ourselves, but generations yet to come, leaving legacies that long outlast our individual lives.